Regression adjustment is a method for identifying the average treatment effect of D on Y under the selection on observables and overlap assumptions. It proceeds in 3 steps. First, we form strata defined by a common value of x, the covariate vector. Next, we compare average values of y between treated and untreated individuals within each stratum. This yields an average treatment effect for a certain kind of person, namely someone with covariates equal to x. We call this the conditional ATE. Finally, we average the conditional ATE over the distribution of x in the population. The final result that we obtain from this process is the unconditional average treatment effect. Here's a very simple example. Suppose we want to estimate the causal effect of dog ownership on lifespan, but we're concerned that women are more likely to own dogs than men. This would be a problem because women on average live longer. To solve this problem using regression adjustment, we would form 2 strata. All the women go into one stratum, and all the men go into the other. We would then compute 2 conditional average treatment effects. One for women, comparing the average lifespan of female dog owners to that of female non-dog owners, and another for men, comparing the average life expectancy of male dog owners to that of male non-dog owners. To obtain the unconditional average treatment effect, we average these 2 conditional average treatment effects with weights that reflect the relative shares of men and women in the population. Now that we understand the idea behind regression adjustment in a simple case, we'll prove that this procedure does in fact identify the unconditional ATE, provided that both the selection on observables and overlap assumptions hold for our vector of covariates x. We'll start by deriving an expression for the conditional average treatment effect. And to do this, we'll calculate the expectation of y given x and d. Now remember our expression for y in terms of potential outcomes from before. Substituting this in, and using some of the basic properties of expectation, we end up with the expectation of y0 given x and d, plus d multiplied by the difference of conditional expectations, y1 given x and d, minus y0 given x and d. Now here's where we're going to use our selection on observables assumption. This tells us that once we've conditioned on x, we can drop d from the conditioning set for both the potential outcome y0 when untreated and the potential outcome y1 when treated. This means that the conditional expectation of y given x and d is equal to the expectation of y0 given x plus d times the difference of conditional expectations, y1 given x minus y0 given x. Now let's take a closer look at d. If we set d equal to 1, then we will discover that the expectation of y given x, comma d equals 1 is equal to the expectation of y1 given x. That's because the first expectation of y0 cancels with the second. On the other hand, if we set d equals to 0, then the entire second term in the expression disappears, and we're left with the expectation of y given x and d equals 0 is equal to the expectation of y0 given x. We now have all the ingredients we need to calculate the average treatment effect conditional on x. Just take the difference of the 2 expressions in the box. We discover that the expectation of y1 given x minus the expectation of y0 given x, which is by definition the conditional ATE, is equal to the expectation of y given x and d equals 1 minus the expectation of y given x and d equals 0. We've already used the selection on observables assumption, Now it's time to use the overlap assumption. The result we've just derived gives us a way to calculate the conditional average treatment effect in terms of two observable expectations. The first is the conditional expectation of y given x and d equals 1, and the second is the conditional expectation of y given x and d equals 0. For this conditional average treatment effect to be well defined at a particular value, little x, of the covariate vector x, both of these conditional expectations need to be well defined. For that to be the case, there need to actually be some people who are treated and have that particular value of covariates, and some people who are untreated and have the same value of covariates. This is precisely what the overlap assumption guarantees, because it tells us that for any value of the covariates x, there are some people who are treated and some who are not. We've come to the last step of our derivation. All that remains is to use iterated expectations to convert our result for the conditional average treatment effect into one for the unconditional average treatment effect. By definition, the ATE is the expectation of y1 minus the expectation of y0. Applying iterated expectations over the distribution of x, we can write this as the expectation of y1 minus y0 given x. Now, by linearity, the inner expectation can be split into two separate expectations, that of y1 given x and y0 given x. And now we recognize the expression that we derived in the red box above. This is just the conditional average treatment effect. Because we've already derived an expression for the conditional average treatment effect in terms of observed expectations, namely that of y given d equals 1 and x, and y given d equals 0 and x, we're done. To summarize, under the selection on observables and overlap assumptions, regression adjustment allows us to identify the average treatment effect in 3 steps. First, we form strata, such that within a given stratum, all individuals have the same values of the covariates x. Next, we calculate conditional average treatment effects within a given stratum. In other words, for a particular value of x, we compare treated and untreated individuals. Finally, we average these conditional treatment effects over the distribution of x in the population to convert them into an unconditional effect.